go. All right, this is lesson 9 for pre-calculus. Today we're doing sections 11.2 with a little bit of 11.4. It's vectors in 3 space and then lines in 3 space, so in 3 dimensions. So vectors in 3 dimensions, lines in 3 dimensions. So let's just go ahead and jump right in and start talking about vectors in 3 space. So let's say here we've got vector v has an initial point at 3, -2, 6, 3, -2, 6, and it has a terminal point at 1, -5, 7. Let's talk about what we know about this vector. So just like in 2 space, right, it goes from initial point to terminal point, right? It's a line, it's a directed line segment. I'm not gonna make you watch me graph this because it's terrible, like I'm awful at graphing in 3 space. But what we just do here is we say, all right, so if I start at 3 and I go to 1, the component form is -2 for the x's. So the x changes by -2. If I start at -2 and I go to -5, -3 is my y change. If I go from 6 to 7, that's a +1, it's a +1. So to find the component form, basically it's just the same as the component form for 2 space, for 2 dimensions, for x and y. It's just you're gonna add in the extra one, z. So say, all right, starting here, going there, like from initial to terminal, what's a change in x, a change in y, a change in z, directed change, so positive or negative. So that is our component form for vector v. Now we could be asked to find the magnitude of v, just like we found magnitude in 2 space. So here, if we're looking for magnitude of v, remember magnitude is with these double absolute value brackets. So the magnitude here is basically just the distance formula in 3 space. So here, it's the change between the initial and terminal point, or the x component squared, plus the change in y, or the y component squared, plus the change in z, or the z component squared. Remember, the magnitude is just the length of this directed line segment, or the length of this vector. So it's just the distance from, well, initial terminal point. So here it's just going to be the square root of 4 plus 9 plus 1, right? 4 and 9 make, or sorry, that's just 14. So here it's just square root of 14. So the magnitude of v is just 14. So now if I want to find a unit vector, let's say we want a unit vector u in the direction of v. What we do here is just say, well, u equals vector v divided by the magnitude of vector v. So here it's just the unit vector is 1 over the square root of 14. We can rationalize that if we want, times -2, -3, 1. And scalar multiplication in 3 space works just the same way it does in 2 space with vectors. We just distribute this through. So here, right, this is, we want to rationalize 1 over root 14, right? We multiply it by square root of 14 over square root of 14. That gives me square root of 14 over 14. We can use that. So it's the square root of 14 over 14. Multiply it through to get our unit vector u equals -root 14 over 7, because 2 over 14 is going to give us an over 7 there. Negative square root of 14 over, sorry, square root of 3 square root of 14 over 14. And then just positive root 14 over 14. You can leave your answer like that if you want. That's fine. I'll accept that. Okay, so vectors in 3 space. basically all the stuff that we learned in 2 dimensions still holds in 3 dimensions. Yeah, you should be able to do these. Not too bad. Let's move on to linear combinations, which is scalar multiplication with addition, subtraction. Then we'll talk a little bit of dot product and angles between. And those are all going to be just like in 2 dimensions. Now, while I'm erasing this, let's chat a little bit. So we have this week, we have next week, and then 1 week after that, and that's it for school. So what's going to happen is you'll get this lesson to do this week, and then I'll make another lesson next week, which will be on sections 11.3 and the rest of 11.4. And then, then the last week, I'll come up with something that's not quite as mathy, not quite as computational. It shouldn't take quite as much time, so that we can finish on kind of an easier note, but still like have some learning involved. So we'll get to that. All right. So let's say we got 3 vectors here. So vector v, new vector v is 4, -7, -2, 4, -7, -2. And remember, we use those little pointy brackets for vectors. So here, let's say we got vector w. That's 5, 7, 3, 5, 7, 3. And let's say we have vector u. That's right, u. U vector. Not a unit vector, just a u vector. 0, 5, -1, 0, 5, negative. Let's make that a 1. There we go. -1. Those look good. All right, so problem A. Let's find v plus 3u minus 2w. All right, so you were able to do these back in chapter 6 when there were just 2 components to each vector. The third one is just adding a third step. He's going to do everything for all 3 numbers. So here we've got v, which is 4, -7, -2, plus 3u. I'm just going to multiply each of those by, each of these, it's dripping, each of these by 3, because it's 3 times u. So here, 3 times 0 is 0, 3 times 5 is 15, 3 times -1 is -3. And then what I'm going to do with this, since it's a minus 2w, I'm just going to write a plus, and I'm going to multiply each of these by a -2. That'll just make it easier to combine everything. It'll make it so I won't forget that negative when I'm combining. So here that -2 is going to go here, multiply to get -10, -14, -6. That's -2w. So I did the scalar multiplication, multiplied each number through, and I'm just going to combine the components. All right, so it's just regular addition. I have 4 plus 0 plus -10. That's going to give me a -6. I have -7, 15, -14. That's going to give me -6. I just made these up. I didn't actually do these problems yet. So, hey, look, there's 2 -6s. And then -2, -3, -6. That's going to give me -11. There it is. That's it. Yep. All right. Hopefully you got that. All right, let's say we got something like this. Problem B. There's Emma. It's written like this. So I'm not saying it while I write it, because I want you to take a moment and I want you to say it. What does that mean? Just say it to your computer. It's kind of silly, I know, but just say it. I mean, I'm talking to my phone right here, so I'm being silly too. But just say, like, what is that? That is, right, it's the magnitude of 2v plus w. So what we're going to do is we're going to find what vector is 2v plus w, And then we're going to take the magnitude of that. I remember back in chapter 6, we had some problems similar to this. And some people took the magnitude here and the magnitude there and then added those together. That's not what we're doing. If that was, then we'd have magnitude symbols around each one. So it's kind of like parentheses. Do the stuff inside first and then take the magnitude. So 2v, so here I've got magnitude of 2v, which is going to be 8 comma negative 14 comma negative 4, plus w, which is 5 comma 7 comma 3. All right, so I'm just going to add these. So it's magnitude of this vector, which is 13 comma negative 7 comma negative 7. And I'm going to find the magnitude of that now. So that's going to be the square root of 13 squared plus 7 squared plus 7 squared. I can ignore the negatives because negative 7 squared is the same as 7 squared, so I can just write 49 either way. Right, so it's the square root of 169 because it's 13 squared plus 49 and 49. That's 98, which is going to give me, what, 267? So it's the square root of 267. Might want to check that with the calculator. You get the idea. Okay. All right, let's move on to dot product. Dot product. So let's go to problem C here. And problem C is V dot W. V dot W. Remember the dot product? Yeah, dot product. Dot product was pretty simple, right? The dot product just says to multiply each corresponding component, boop, 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 and then add those products together. So I'm going to go for V dot W, I'm going to go 4 times 5. So the x's times the x's, plus negative 7 times 7. So the y times y, plus negative 2 times 3, the z times z. So negative 2 times 3. So this gives me 20 minus 49 minus 6. This is negative 55, and 20 gives me negative 35. And that is V dot W. That's a dot product in 3 space. It's just, this is a dot product in 2 space, right? It's just multiply the x's, multiply the y's, add them together. Just throw in the z's. Product of the z's, add that in. There's your dot product. Cool. So now, let's find the angle between V and W. Right, this is all stuff we did with 2-dimensional vectors. So I'm kind of going maybe a little bit quick through it, but if you're struggling a little bit, right, I got office hours Monday through Friday. Nobody comes to them, so you're welcome to come to them if you have questions. All right. So problem D, I want the angle between V and W. So that, in order to find that, one of the ways to find this is using the same formula as we did with 2-space back in chapter 6. So it's cosine of the angle equals V dot W, so that dot product, divided by the magnitude of V times the magnitude of W. So if this was a new problem, I would find the dot product of V dot W. I know V dot W is 35. So I've got cosine of theta equals 35 divided by, and then I'm going to find the magnitude of V and the magnitude of W. I'm going to use my calculator for this because, well, you know, why not? Well, let's go. Let's just do this. V square root of 16 plus 49 plus 4, that's 20, 69. So square root of 69, and then W, magnitude there is going to be 25 plus 49 plus 9. What's that going to be? 58, 60, 78, 93. I'm going to double check that one because Although I'm a math teacher, I do goof sometimes. 83, I threw an extra 1 in there. So square root of 83. Did I say 93? I don't remember. Okay, regardless, I'll double check this other one too. 16 plus 49 plus 4. I got that one right. Cool. Alright, so here, this is not our answer. Not yet. We want theta. We want the angle between them. So what we need to do is we need to take the arc cosine or the inverse cosine of each side. So theta equals cosine inverse of 35 over square root of 69 times square root of 83. And use a calculator. And here, let's just, since it's an angle between two vectors, we're not talking unit circle stuff, let's put it back in degrees, just because degrees are really easy to think about. Like, you can kind of visualize them a little bit easier. So, mode, degree, and let's go inverse cosine of 35 over square root of 69 times square root of 83. Move it over, boom! And I get about 62.45 degrees. So it's about 62.45 degrees. If you were in radian mode, let's just see, which is fine if you're in radian mode. Second. There it is. Boom. It's about 1.09 or 1.09 radians. There, you could have multiplied that by pi and divided by 182 if you want to. Okay, cool. That's the stuff that you're going to be asked to do more or less, which is a set of vectors or a few vectors. So you'll be asked similar questions on the assignment. Be ready for those. I think you'll be fine. It's the same stuff that we did in chapter 6. It's just we threw in an extra component. All right. So now we're going to talk about vectors in 3 space. How they're orthogonal, which right, remember, means like perpendicular, but perpendicular in 3 space. So if they are orthogonal or if they are parallel, what that means for each of them and how to find it. Okay. Okay. Let's say, okay, let's just write up some stuff here. So V and W are orthogonal if and only if V dot W is 0. Remember, that's what we said back in 2 space. When we're dealing with 2-dimensional vectors. If the dot product is 0, they're orthogonal. If they're orthogonal, dot product is 0. Right? They're perpendicular. But if you're, right, you can be perpendicular like this. You can also be perpendicular like in any direction, right? As long as they're just, doesn't matter, right? There's another fun move that you, sorry, couldn't do it from, because coronavirus. But dance move, right? Perpendicular. Now, parallel, V and W are parallel if and only if vector V equals some number, some constant, times W. So their component forms, right, are scalar multiples of each other. It can be positive or negative, just as long as C is some number, or C is just some number in the real, some real number that's not 0. We're going to kick out 0. I mean, maybe 0 is parallel to everyone, but let's not worry about that. Okay, so let's work with this a little bit. Let's say we've got vector V here, which is 4, -7, -2, 4, -7, -2, same V vector as before, I believe. And let's say here we've got vector Z, or Z, depending on where you are. Vector Z is 10 BC. It's not a date. We don't know what B and C are. It's not like BC. It's not in Vancouver either. BC. Doesn't matter. Sorry. So we're going to find the values of BC that make, so find B and C, so V and W, my goodness, V and Z are orthogonal, and find B and C, so V and Z are parallel. Okay, so what you do here, you're like, all right, there are multiple possibilities for what B and C could be in this one. We just need to find some numbers that work. We don't necessarily need a whole set of numbers. We just need to find some that work. So here, I've got orthogonal, which means V dot Z equals 0. Emma thinks so too. Isn't that right, Emma? Maybe not. There she is. So, I'm going to take the dot product. 4 times 10 is 40. Minus 7b, because the negative 7 times b. And then minus 2c equals 0. Alright, so let's just like get a relationship between b and c, and then we just put in a number for b and find a number for c. So let's solve for b. Let's get b equals. So I'm going to say b equals at the end. B equals something with a c. So here I'm going to subtract a 40 and add a 2c over. So negative 7b equals 2c minus, not equals, minus 40. And I'll divide by that negative 7. Divide by negative 7. All right. So I have b equals 2c minus 40 over negative 7. And there are infinitely many numbers that could satisfy that linear equation. So, let's think of some that might be nice. Like if I make c negative 8, so let's say c equals negative 8. I'm just doing that because 2 times negative 8 would be negative 16, right? Which gives us negative 56 over negative 7, right? Then we get b equals positive 8. So 40 minus 56 plus 16 would give us 0. Yeah, cool. That works. Basically, the thing I want you to grab from this is if they are orthogonal, set up your equation, your dot product equation equal to 0 and solve. The problem on the assignment will be slightly easier than that. All right, let's do this one. Parallel. Not a single L, a parallel. Like 2 of them. Just kidding. Well, I don't even know what a L is. But I do know what a parallel is. Well, not a parallel, when vectors are parallel. Vectors are parallel if Z is a scalar multiple of V, or vice versa. So here, basically, I gotta say, well, C times 10 comma B comma C, or let's just make this, what letter should I use? I don't know. X, whatever, it's just a number. That equals 4 comma negative 7 comma negative 2. Well, here I've only really got one thing that matches up. I've got 10x equals 4. So I need to figure out what x is. Ooh, I got a better idea. You know what? This is going to be too complicated. Let's move that x over there. Yeah, let's do that. X. So 4x equals 10. Yeah, much better. That way if I can find this constant, I can just multiply by those. Sorry, not thinking straight. Okay, so 4x equals 10, divide by 4. That gives me x equals 5 over 2, or 2.5. So b is going to be x times negative 7. So negative 35 divided by 2. Right? Because 5 times 7 is 35 over 2. And then c is going to be negative 2 times 5 over 2, which is just negative 5. In other words, all of these have to be 2.5 times bigger than those, because 10 is 2.5 times bigger than 4. So for two vectors to be parallel, basically one of them has to be a number times that vector to get the other one. So this equals 2.5 times that, parallel. Perpendicular, sorry, not perpendicular, orthogonal means their dot product is 0. Okay, so that's it for mostly for vectors. We're going to talk a little bit about lines now, and that'll be it for the lesson. Hopefully this hasn't gone too long. I'm not really timing myself. Okay. So lines in 3 space. So because we have 3 dimensions here, what we're going to do is we're actually, there's a couple things we can do. We can write a set of 3 parametric equations, and then from that set of 3 parametric equations, what we do is we're going to introduce a new variable t. We can solve each of those for the variable t, so like t equals t equals t equals, and then we can have a symmetric set of equations where it's only in x, y, and z, but they're all equal to each other. So it's like 3 equations equaling each other instead of just like 1 equal sign, there's 2 equal signs and 3 expressions. So we are going to write the set of parametric and set of symmetric equations for a line in 3 space. I'm going to do 2 examples of this. One example is where we have a point that the line goes through. Let's make this point 4, negative, oh my goodness, not that, there we go. Negative 3, 5, 2, negative 3, comma 5, comma 2. And then the line is parallel to the vector v, good old vector v, which is 4, negative 7, negative 2. Okay. So basically what this says is that our x's are going to go, they're going to start at negative 3. And then every time we go like 1 step, they're going to increase by 4. Because we have a 4 component on our x. So start at negative 3. Like if t was 0, no change. We just start at negative 3. That's our starting point. And then we go 1 step. Whatever that step is, doesn't matter. We just want something constant so we can do the same change for all of these. We're going to go 4 in the x direction from that negative 3. So that gives us our x's. Now, what we're doing here is we're saying we're taking the direction from the vector. And we're starting at this point. So these are our starting points for our x, y, and z. And then this is kind of like the x slope, y slope, z slope. Kind of. And then as one of them changes by an amount, we keep that amount, whatever t is, doesn't matter. But it's just, this t is constant for all of them. So as x changes by 4, y will change by negative 7, and z will change by negative 2. So that way they're all changing at this collective rate. So that's our x equation. Our y equation, y equals, start at 5 and subtract 7 every t interval. And then z equals, start at 2 and subtract 2 every t interval. This is the set of parametric equations. Parametric equations. So that's a set of parametric equations for the line. That's it. That's all you gotta do. Now, in order to find the symmetric equations, what we do is we're gonna solve each of these for t. So I'm gonna go like plus 3 divided by 4. So here, t equals x plus 3 divided by 4. Here, t equals y minus 5 over negative 7. Subtract and divide. Here, t equals z minus 2, let's make it a 2, divided by negative 2. So now, because that t is the same t for each of these, all of these equal t. So all of these three expressions all equal each other. And that's how we come up with our set of symmetric equations. We just write x plus 3 over 4 equals y minus 5 over negative 7 equals z minus 2 over negative 2. And that's it. That's all it is. So that's the symmetric equations. So when you're writing an equation from a point and a parallel vector, you take each component, x, y, z, the start at that point, and then the change comes from that parallel vector. That gives you your parametric equations. Solve each of those for t. That gives you your set of symmetric equations. We're going to do one more example just to really let this sink in. This is something new, which is why I'm doing a couple examples with it. Whereas the vector stuff, it was the same as what we did in chapter 6. We just put in an extra component, the z component. All right. So one more, that's it. And then you got it. Okay, dry this off. Dry. Okay, all right. Let's say we have 2 points that we're going to put a line through. So in this case, we don't have the parallel vector. We just got 2 points. Right? That's all you need for a line. So we got 3, negative 2, comma 9. That's 1 point. And the other point is 8, comma 2, comma negative 1. Okay. So what we're going to do here is we're going to use these 2 points to find the vector between them. So we're going to assign one of them as the initial point. Doesn't matter which one, just pick one and make that your initial point. I'm going to make this one my initial point. Why? Because I wrote it first. Doesn't matter. So I'm going to make the vector that goes this way. Starts here, ends there. So my vector, and this is the vector that I'm going to use to write my equations. So I'm going to go from 3 to 8, which is 5, positive. Negative 2 to positive 2, which is 4. So 5, 4. 9 to negative 1, which is minus 10. So that is the vector that's parallel to this line. It's a vector that would go right along this line. It's a vector that connects the points. So I'm going to write my set of parametric equations, my set of symmetric equations from this. And because I chose this as my initial point, I'm just going to choose it again to write my equations. It'd be the same. It would work just as well if I chose my terminal point. Doesn't really matter. But I'm going to choose this one, 3, negative 2, 9. So for my parametric equation,